Let's discuss problem F now. Even though it's rated F, it's not that hard. You can read the statement now or listen to my explanation. So in my explanation, there are n numbers, an array of n integer numbers. We can do two operations. One operation is choose a number and replace it with itself divided by 2 and rounded up. The second operation we can make is choose a number, replace it with itself minus b, maximum of this and 0. You see it on your screen. We can do no more than k1 operations of the first type, no more than k2 operations of the second type. But for every element of the array, you can apply an operation of specific type only once. And we want to minimize the sum of the array. You need to just output the minimal possible sum we can achieve. In this problem, we have an exponential amount of choices we can make, of numbers we can choose for the first operation and for the second. So it usually means that we can make some greedy assumptions, some greedy simplifications of the problem to narrow down our freedom of choice by stating that we can only look at answers in some specific shape. So let's try to find some assumptions we can make about this process. First of all, let's consider the order in which we do the operations of different types. Consider a number a, to which we do the operations of both types. There are two variants, two options. You can first subtract b, take maximum of this and 0, then divide by 2 and round up. Or you can first divide by 2 and round up, and then subtract b and take maximum of this and 0. Well, let's transform this expression. So first of all, this expression, we can put this division by 2 under the parenthesis of max. So it's maximum of a minus b over 2 and 0. And we can clearly see that it's the same as writing this, maximum of rounding up of a minus b over 2 and 0. Well, because if it's less than 0 or equal, then this will be 0, this expression will be 0, and this will also be 0. But if it's greater than 0, then of course we'll take this and round it up, and so we will do here. So those are always equal. And let's also transform this expression. For this expression, we'll just put b under the parenthesis of rounding up, because b is integer. Let's also put b into the numerator. So now it's clear that this is never less, yes? This is always larger or equal, because we take a minus b, and here we take a minus 2b, and then apply a sequence of non-decreasing functions. First of all, division by 2 is non-decreasing, it's a non-decreasing function. Then rounding up is also a non-decreasing function because it has such a graph, never decreases. And then we take maximum of this and 0, which is also never decreasing because this function has such a graph. It's 0 for negative numbers and it's equal to x for positive numbers. Yeah, so it's also never decreasing. So this will be always not less than this. So if we want to minimize the sum, we always want to first divide by 2 and then subtract b. So our first simplification is knowing that we need to first apply the operations of type 1 and then the operations of type 2. Now suppose we already know the best way to apply the operations of type 1. Suppose we already divided some of the numbers by 2, and now we want to know what's the best way to apply the operations of type 2. But I think it's pretty obvious that we need to apply the operations of type 2 to the numbers that are currently the largest. Well, because the larger the number is, the more you can subtract from it, potentially. Of course, if it's less or equal to b, then you will just subtract its whole value from the sum. But if it's larger or equal to b, then you subtract b. So the amount that you subtract, the graph of this amount looks like this. Yeah, up to b. So it's never decreasing, as you see. And so the larger the number is, the more you can subtract, at least not less. So of course, if you want to decrease the sum of the array as much as possible, you need to subtract from the largest numbers. Okay. Suppose we initially sorted the array in the decreasing order. And then we chose some of the numbers that we want to divide by 2, and then sorted it once again in the decreasing order. And obviously, some of the numbers that we used to divide change their position. They now occur later in the array. So I will not draw this arrow. Just know that both of those arrays are in decreasing order. So this is the initial version of the array, and this is the new version of the array after the operations of type 1. And those numbers are now occurring later in the array because they were decreased. Now we know that we'll take the largest k2 numbers and subtract b from them. Suppose there is at least one number to which we apply the both operations. So it was divided, and then we will subtract from it. Let's prove that this must be the highest number. Or let's rather prove that if the highest number is not divided, then we can change the answer so that it will be divided. So suppose the largest number was not divided by 2, and some other number was divided by 2 and then also subtracted. We will change the answer in the following manner. We will not divide this, instead we'll divide this. And subtract from it. Let's see how the sum changed. So we know that this number is larger or equal to this number. Let's say we have a number a1 and a2. a1 is larger or equal to a2. In the first scenario, we used to subtract b and take max of 0 on this from a1. And we used to subtract b from a2 over 2 rounded up and take max of 0 on this. In the second scenario, we do the opposite. Let's see which of those two sums is larger. Let's draw a diagram. So a1 over 2 will be this height. I mean a1 over 2 rounded up. And this height will be a2 over 2 rounded up. As we know, it's less or equal. Also, let's draw the full a1 here and the full a2 here. As we know, a2 is also less or equal to a1. There are several possibilities. The first case is when b is larger or equal to this, which means that line b, the height b, will go along this line or higher. Of course, it can also go higher than that. In the first scenario, the remaining sum will look like this. Because before you subtract b, you will have this number and this number. After you subtract b, this number becomes 0, and this is what's left of it. In the second scenario, you have this number and this number before you subtract b. So this number will become 0, and this what remains. So in the first scenario, this is what the sum will be equal to, and in the second scenario, this is what the sum will be equal to. Of course, this is less or equal. So in this case, when b is larger or equal to a1 over 2 rounded up, this will be less or equal. The second case is when b is less or equal to a2 over 2 rounded up. So line b goes somewhere here. The first sum can be shown as this plus that, and the second sum is this plus that. The total amount which we subtract from the sum, the initial sum, is 2b in both cases, plus a1 over 2 rounded down in the second case, and a2 over 2 rounded down in the first case. So in the second case, we will subtract more or the same amount. So again, in this case, this is larger or equal. And the last case, if b is between the two numbers, a1 over 2 and a2 over 2, so line goes somewhere here. In this case, in the first scenario, we subtract this amount from the original sum plus 2b, because this number will become 0, and this number will become this height. So the overall amount we subtracted is this plus 2b. While in the second scenario, we subtract this plus 2b. This is equal to a1 over 2 rounded down, while this is something less or equal to a2 over 2 rounded down, which is less or equal to a1 over 2 rounded down. So again, it means that in the second scenario, we subtract from this more from the initial sum. So this is again larger or equal. So in all cases, this sum will be larger or equal to that sum. So it's never worse to do the second scenario, which means that if we apply both operations to one of the numbers, but it's not the largest number, means we can change the answer so that we apply both operations to the largest number. And then we can fix it and ignore it for a while. Fix the fact that we apply both operations to the largest number. And considering this, let's ignore this number, and let's again see if we still have another number to which we apply both operations, and it's not the largest number, we can keep applying this logic so that the answer becomes such where both operations are applied to the largest initial numbers. So if we know that we apply both operations to p different numbers, we can be sure that we can consider only the answers where those p numbers are the largest initial numbers. And now it's time to change the image with which we work to draw the initial array in the decreasing order. We know that the numbers to which we apply both operations are p largest numbers. Of course, we don't know the p, but it's just some number. Maybe it's 0. So those p numbers are the ones to which we apply both divide and subtract. Divide and subtract. To all the other numbers, we will either apply divide or subtract. Or nothing, of course. First of all, it's pretty obvious that we apply nothing to the smallest numbers. So if we apply nothing to one of the numbers, but then we apply some of the operation, to a smaller number, we can always start applying this operation to this larger number. And of course, the sum will decrease, or at least not increase. We already shown it with subtraction. Of course, if you divide a larger number, you will decrease the sum more than if you would divide a smaller number. So, of course, with division, it also works. So, of course, we already know that we need to apply k1 minus p more operations of the first type and k2 minus p more operations of the second type. So we can consider those k1 plus k2 minus 2p consecutive elements in the decreasing order. And we know that we must apply an operation of type 1 or type 2 to each of them. Now we just need to know which operation, where to apply which operation. Let's focus on this part of the problem specifically and ignore the rest for now. So let's say we have k1 plus k2 minus p minus 2p. Elements, to each of them we apply either a subtraction or a division. And we know that there must be exactly k1 minus p divisions, k2 minus p subtractions. Let's separately consider numbers that are less or equal to b and those that are greater to b. Of course, those that are less or equal to b will be in the tail of our array because we sort it in decreasing order. What we can say about those numbers that are less or equal to b? We can say that those of them from which we subtract b will become 0. So the overall effect that those numbers have on the final sum consists only of those numbers that we chose to divide by 2. So the overall effect of this part of the array on the overall final sum is just those numbers that we chose to divide, divided by 2 rounded up. So of course, we'll divide the smallest numbers. If we know that 3 elements from here must be divided, we know that these are those 3 elements. And now what we can say about those numbers that are greater than b. We know that if we decided to subtract, let's say, from 3 numbers and to divide the rest, we know that the overall amount that will be subtracted from the initial sum will be 3b, because from each of the numbers which we decided to subtract from, we will subtract exactly b. And from all the other numbers, we will subtract themselves divided by 2 rounded down. So the overall effect of our choice is 3b will be subtracted and plus the sum of all such values. If we want to subtract more, of course we want to maximize those values. This does not depend on which 3 numbers we choose. So we just want to maximize this. So of course we decide to subtract from the smallest numbers to divide the largest, to subtract more. And so the answer to this part of the problem will look like this. Meaning that the answer to the initial problem looks like this. there will be p largest number to which we apply both operations, divide and subtract. Then there will be, let's call it q, several consecutive numbers to which we apply only the division. Then there will be this amount. This amount is k1 minus p, consecutive numbers to which we apply only the subtraction, and then there will be the remaining k2 minus p minus q, consecutive numbers to which we apply again only the division. So the only freedom of choice that's left is p and q. We can choose any p and q as long as, first of all, this is not negative, this is not negative, and also this is not negative, the part where we do not apply anything. And this part is n minus k1 minus k2 plus p. So those are the inequalities. The bounding inequalities. This is not 0, this is not less than 0, this is not less than 0, this is not less than 0. Giving those constraints, also this is not 0, not less than 0, this is not less than 0. Giving those constraints, we can pick any p and q, and such p and q will correspond to a single possible candidate for the best answer. And the constraints to the problem allow us to just iterate through all the possible pairs of p and q, thus solving this problem in n squared time. Of course, we need to check each candidate in O of 1, but this is very easily done using just prefix sums. Let's look at my solution. So in my code, I first of all read all the input, then I sort the A in the decreasing order, and then I calculate the three arrays. A subtracted is what an ith element will be if we decide to subtract from it. A halved is the same, but if we decide to divide it by 2, and A halved and subtracted, what the ith element will be if we decide to divide it by 2 and subtract from. And then we calculate 4 prefix sum arrays for A subtracted, for A halved, and for A halved and subtracted, using the same function written here. Now we just fix all the valid P's, all the valid Q's, according to the inequalities I wrote, and then check this candidate. We take the first P halved and subtracted, then the next Q only halved, then the next K2 minus P only subtracted, and then the next K1 minus P minus Q halved and subtracted. And then we take the remaining numbers as they are without changing them. This is a candidate for the answer. Now we just pick the best candidate and output it. And this is accepted. We could also solve this problem in n log n time if we notice that if we denote f of p as the best answer for such p, for such specific p, if we notice that this function is convex, meaning that the change in its value with each following p increases. So the change from this p to the next p is, for example, -10, then it's -8, then it's -4, and then it's 0, for example, and then it becomes positive, for example, 2, 4, 6, and so on. So it always increases. The change always increases. There is no proof for it, but it's true that f of p is convex. And using the fact that it's convex, we can just find the first p such that the change from p to p plus 1 in the value of the function is not negative. And this will be the optimal p. We can find such p using binary search. So we find the best answer for such p and for the next p, for p plus 1. If the change is not negative, we find such first p, and this is the best p. Anyway, that's it for today. I remind you that I give private lessons on competitive programming. If you're interested, contact me on Telegram. Goodbye.